Beyond the boundaries of human perception, across distances that dissolve meaning from numbers, something lurks that defies the fundamental laws we thought governed reality. When astronomers first measured its dimensions, they ran their calculations repeatedly, convinced their instruments had malfunctioned. But the instruments were working perfectly. What they had discovered was an impossibility made manifest, a violation of cosmic limits we believed absolute. This is an expedition to the uttermost edge of what the universe permits to exist, to a realm where gravity grows so overwhelming it doesn't merely bend space-time but shatters it completely. We're going to voyage backward through time's river, rushing across billions upon billions of light years to observe something from the universe's infancy, from an era when galaxies were raw and newly born, when the cosmos churned with violence we can scarcely imagine today. The entity bears the designation TON 618. Within its core spins a black hole containing the mass of 66 billion suns, all crushed into a zone whose outer edge would stretch 40 times beyond Pluto's distant orbit if you could somehow transplant it to replace our star. It blazes with the combined brilliance of 140 trillion suns, making it among the most luminous phenomena in the observable universe, despite the staggering fact that its light has been travelling toward us for 10 billion years. When that light first departed on its journey, Earth was nothing. The sun was not even a glimmer in a molecular cloud. The universe had lived through barely 1/4 of its current lifespan. Let us embark. That luminous river flowing across our darkness above is the Milky Way, the galaxy we call home, containing several 100 billion stars in its spiral embrace. Hidden somewhere within that stellar ocean lies Sagittarius A star, a supermassive black hole packed with 4 million times our sun's mass, the gravitational anchor around which our entire galaxy rotates. By conventional standards, it represents something colossal, but our destination contains 16,000 times more mass. Our target does not reside in this galaxy, not remotely close. To arrive there, we must abandon every star your eyes can detect in Earth's night sky. We must transcend the local group of neighbouring galaxies, surge past the Virgo supercluster, leave behind every familiar landmark in the cosmos. We must shatter the cosmic speed limit itself. As we accelerate beyond light speed in this thought experiment, the Milky Way diminishes behind us into the void. Its spiral architecture becomes visible, displaying elegant curved arms sweeping through space, dark lanes of dust weaving between them, brilliant regions of active star formation scattered throughout the galactic disk like jewels. Other galaxies begin to materialize around us. The large and small Magellanic Clouds appear first, our satellite galaxies orbiting us like moons around a planet. Then Andromeda emerges, our nearest, large spiral companion containing perhaps 1 trillion stars, rushing toward us on a collision course that will consummate in 4 billion years. We push onward into the abyss. Additional galaxies reveal themselves in growing numbers. Dozens multiply into hundreds. Hundreds become thousands. Each one houses hundreds of billions of stars. Each star potentially hosts planets. Each planet might cradle life. Yet humanity has never intercepted a message from another technological civilization. Perhaps we stand alone in this vast darkness. Or perhaps the universe stretches so incomprehensibly far that civilizations simply cannot locate each other across the cosmic emptiness, their signals dissipating into noise before crossing the unbridgeable distances. Now we penetrate true intergalactic space, the voids between galaxy clusters. Regions so profoundly empty you could traverse millions of light years without encountering a single star, a single planet, a single speck of matter larger than drifting atoms. The temperature in these regions hovers just barely above absolute zero, warmed exclusively by the faint afterglow of the Big Bang itself. That ancient light stretched and cooled by cosmic expansion until it exists as microwave radiation. But the darkness proves temporary. points of light begin materializing in the void, scattered initially, then multiplying exponentially until they saturate every direction we look. Galaxies, thousands upon thousands of them, millions of them. These galaxies don't scatter randomly through space, but organize themselves into magnificent cosmic architecture, vast webs and sheets and filaments separated by enormous voids containing almost nothing. This represents the large-scale structure of the universe, carved by gravity operating over billions of years as matter flowed along invisible channels of dark matter, clustering into dense nodes while abandoning vast empty spaces between. As we journey deeper, peering further backward through cosmic time, the galaxies undergo a transformation in character. Nearby galaxies appear as mature systems with orderly rotation and modest star formation. But as we push backward through time, galaxies become progressively younger, increasingly irregular, more chaotic. We witness more aggressive star formation, more evidence of violent mergers and gravitational interactions between systems. This makes perfect sense when you remember what we're actually observing. When we examine distant objects in space, we're not seeing them as they exist in the present moment, but as they existed when their light began its journey toward us. Light from a galaxy 10 billion light-years distant shows us that galaxies' appearance 10 billion years ago. We're literally watching cosmic history play out before us, observing the universe's evolution. One point of light ahead grows substantially brighter than its neighbours. This is no standard galaxy. This is a quasar, a cosmic lighthouse beaming across distances so vast they dissolve comprehension, radiating with power that transcends imagination. When astronomers first detected these objects in the early 1960s, they initially believed they were observing peculiar stars within our own galaxy. They appeared as simple points of light, revealing no internal structure even when examined through powerful telescopes. But when astronomers analysed their spectra, measuring the distinctive fingerprints that different elements leave in light, they discovered something that seemed impossible. The spectral lines had shifted dramatically toward longer, redder wavelengths, indicating these objects were receding from us at tremendous velocities, sometimes exceeding 10% of light speed. According to Hubble's law, which relates an object's velocity to its distance in an expanding universe, this meant these objects must be positioned billions of light-years away. If they remained visible across such distances, they had to be radiating incredible amounts of energy, more than entire galaxies containing hundreds of billions of stars. Yet they appeared as dimensionless points, suggesting all this energy originated from regions no larger than our solar system. The energy density exceeded anything previously encountered in nature. The explanation, which crystallized through work during the 1960s and 70s, involves supermassive black holes consuming enormous quantities of matter. As material spirals inward through accretion disks, heating through friction and magnetic interactions, it radiates vast amounts of energy before disappearing forever across the event horizon. This specific quasar, designated TON 618, was initially catalogued at the Tonantzintla Observatory in Mexico in 1957. For decades it remained largely ignored, just one more blue point among thousands captured in stellar surveys. But as observational technology improved and analytical techniques became more sophisticated, astronomers recognized this was something exceptional. The black hole at its heart wasn't merely massive, but ultramassive, ranking among the largest ever discovered in the observable universe. As we approach, the quasar resolves from a point into a disk, then into a vast churning maelstrom of doomed matter. We're now close enough to distinguish the components that make this object shine so brilliantly across cosmic distances. Surrounding the black hole extends an accretion disk spanning thousands of astronomical units, a swirling vortex of material on an inexorable journey toward oblivion. This disk possesses distinct regions with dramatically different properties and behaviours. In the outermost regions, far from the black hole's strongest gravitational influence, The disk resembles a slowly rotating cloud of gas. Temperatures remain relatively cool, just a few thousand degrees, comparable to the surface temperatures of red dwarf stars. Material orbits at a few hundred kilometers per second. The gas remains mostly neutral, not yet stripped off. Its electrons. Moving inward toward the center, conditions intensify dramatically. Gravitational pull strengthens exponentially, and orbital velocities increase accordingly. At a few hundred astronomical units from the center, material orbits at thousands of kilometers per second. Friction becomes intense as different portions of the disk orbit at different speeds, faster inner material grinding against slower outer material, converting orbital kinetic energy directly into heat. Temperatures climb to hundreds of thousands of degrees, then millions. The gas transforms into fully ionized plasma, a sea of free electrons and bare atomic nuclei stripped of their electron clouds. This plasma is threaded throughout with magnetic field lines, generated by the motion of charged particles and amplified through dynamo processes operating within the disk. These magnetic fields play a crucial role in the disk's behavior. They transport angular momentum outward through the disk's structure, allowing material to shed energy and spiral inward toward the black hole. Without this mechanism, material would simply orbit indefinitely, unable to fall inward. The magnetic fields also generate chaos and turbulence. They tangle and twist upon themselves, building up enormous amounts of stored energy, which periodically releases in violent flares and eruptions through magnetic reconnection events where field lines snap and reconnect in new configurations. The disk is anything but smooth and orderly. Instead, it churns violently, plasma boiling under the competing influences of gravity, pressure gradients, and electromagnetic forces. In the innermost regions, within a few tens of astronomical units from the event horizon, conditions become truly extreme. Material orbits at significant fractions of light speed, perhaps 30 or 40%. Relativistic effects become important. Time dilation means processes occur at different rates depending on position within the disk. Distances measured in different directions don't match Euclidean expectations. Space-time itself warps significantly. Temperatures in these innermost regions reach tens of millions of degrees, hot enough that the plasma emits primarily in X-rays rather than visible light. The intense radiation pressure from this emission can actually push back against infalling material, creating complex feedback loops. If too much material tries to fall in simultaneously, the resulting radiation becomes so intense it blows away the incoming material, temporarily shutting down accretion. This creates a natural limit on how quickly black holes can grow, called the Eddington limit, named after the astrophysicist Arthur Eddington who first calculated it. For this ultra-massive black hole, the Eddington limit corresponds to roughly one solar mass of material per year. That might not sound like much, but sustained over millions of years, it allows for tremendous growth. An observation suggests TON 618 is indeed accreting near this limit, devouring material at a prodigious rate. Each kilogram of infalling matter converted partially into radiated energy, with efficiency exceeding nuclear fusion. The accretion disk doesn't exist in isolation. Perpendicular to the disk, emerging from regions very close to the black hole, twin jets of material blast outward at nearly light speed. These jets represent one of the most energetic phenomena in the universe. Narrow beams of plasma and radiation extending for hundreds of thousands of light years, punching through the surrounding galaxy and out into intergalactic space. The mechanism generating these jets involves the black hole's rotation and the magnetic fields threading through the accretion disk. As the black hole spins, it drags space-time around with it, a phenomenon called frame dragging. This rotation, combined with the twisted magnetic fields, acts like a cosmic particle accelerator, flinging material outward along the rotation axis at relativistic speeds. Within these jets, particles reach energies vastly exceeding anything we can produce in terrestrial accelerators. electrons spiral along magnetic field lines, emitting synchrotron radiation across the electromagnetic spectrum. Atomic nuclei accelerate to nearly light speed, becoming cosmic rays that will eventually escape into intergalactic space, perhaps travelling for billions of years before striking some distant world. The jets also carry enormous amounts of energy into the surrounding environment. As they plough through ambient gas, they create vast bubbles and cavities, heating gas and preventing it from cooling and forming stars. This jet feedback represents one way supermassive black holes influence their host galaxies, regulating star formation and affecting galactic evolution. Surrounding the accretion disk and jets, extending for thousands of light years, lies a vast cloud of gas and dust partially obscuring our view of the central regions. This material hasn't yet fallen into the accretion disk, but orbits at larger distances, gradually being pulled inward by the black hole's gravity. Radiation from the inner disk and jets ionizes this gas, causing it to glow with characteristic emission lines that astronomers use to study quasar properties. This obscuring material creates different views depending on viewing angle. If we observe the quasar looking down on the accretion disk from above, we see directly into the bright central regions and observe the full luminosity. But if we view edge-on through the dusty torus, much of the light gets absorbed and the quasar appears dimmer and redder. This orientation dependence explains some of the diversity observed among quasars and active galactic nuclei. The entire structure, from event horizon to outer gas clouds, represents a gravitationally bound system held together by the black hole's immense mass. The black hole itself occupies only a tiny volume at the centre, but its gravitational influence extends across thousands of light years, orchestrating the complex dance of matter spiralling toward destruction. Let us move closer still, approaching the event horizon itself. This boundary represents the point of no return, the surface beyond which escape becomes impossible even for light itself. For this ultra-massive black hole with 66 billion solar masses, the event horizon has a radius of approximately 1,300 astronomical units, roughly 40 times Pluto's orbital distance from the Sun. To put this in perspective, if you could place this black hole where our Sun sits, its event horizon would extend far beyond the orbits of all the planets, beyond the Kuiper belt, reaching into the inner Oort cloud. The entire planetary system would lie deep within the black hole's gravitational trap. But don't imagine the event horizon as a physical surface, some kind of membrane or barrier. It's simply a demarcation in space-time, a mathematical boundary where certain geometric properties change discontinuously. An observer falling through an event horizon of this size would notice nothing special at the moment of crossing. No wall, no sensation, no indication they had passed the point of no return. The transition is absolutely smooth. However, the situation inside differs profoundly from outside. Outside the event horizon, it remains possible, at least in principle, to escape if you have sufficient velocity. You can orbit the black hole, maintaining a stable position. Time proceeds normally, space behaves as expected. Inside the event horizon, the geometry of space-time itself transforms. The direction toward the singularity becomes time-like rather than space-like. This means falling toward the singularity becomes as inevitable as moving forward through time. You cannot stop it, cannot reverse it, cannot even slow it down, any more than you can prevent time from advancing. The singularity lies in your future as inexorably as tomorrow's sunrise. From outside, we can never witness events occurring inside the event horizon. Light emitted inside cannot escape to reach external observers. If we watch something fall into a black hole, we see it approach the horizon, growing ever dimmer and more red-shifted, apparently slowing down, asymptotically approaching the horizon, but never quite reaching it. Time dilation becomes infinite at the horizon, causing infalling objects to appear frozen in time from our external perspective. But this is purely an observational effect due to light travel time and gravitational time dilation. From the perspective of the infalling object, nothing special happens at the horizon. It crosses smoothly and continues falling inward toward the singularity, reaching its final destination in a finite time as measured by its own clock. The region just outside the event horizon has special properties. There exists a zone called the photon sphere, where gravity is strong enough that light can orbit the black hole. At exactly 1.5 times the Schwarzschild radius for a non-rotating black hole, photons can travel in circular orbits. Inside this radius, but outside the event horizon, lies a region where circular orbits become unstable. Any small perturbation causes orbiting material to either escape to larger radius or fall into the black hole. For a rotating black hole, which this certainly is given its formation history and ongoing accretion, the situation becomes more complex. The rotation drags space-time around, creating a region called the ergosphere where nothing can remain stationary relative to distant observers. Everything in the ergosphere, even light, must rotate in the same direction as the black hole's spin. This frame-dragging effect creates interesting theoretical possibilities, like the Penrose process, where energy can theoretically be extracted from a rotating black hole's rotational energy. The event horizon for a rotating black hole is slightly smaller than for a non-rotating black hole of the same mass, and the geometry near the horizon becomes more complex. There's actually an inner and outer horizon, with a region between them called the Cauchy horizon, where quantum effects likely become important. But these subtleties remain theoretical since we cannot observe them directly. As we approach even closer, we must consider what actually happens to matter as it crosses the event horizon. For stellar mass black holes, tidal forces become extreme even before reaching the horizon. The difference in gravitational pull between an object's near and far ends grows so large it tears the object apart, a process called spaghettification. Your feet, being closer to the black hole, would be pulled far more strongly than your head, stretching you into a long, thin strand before ultimately ripping you apart at the molecular level. But for an ultra-massive black hole like this, the situation is remarkably different. Because the event horizon is so enormous, the curvature of space-time at the horizon is actually quite gentle. The tidal forces at the horizon are relatively weak, far weaker than at Earth's surface. A human falling through this event horizon would experience nothing unusual, no crushing forces, no tearing. They would pass through smoothly, perhaps not even realizing they had crossed until attempting to turn back. This is one of the profound ironies of black holes. The more massive the black hole, the gentler the conditions at its event horizon. For supermassive and ultramassive black holes, the event horizon represents a remarkably benign place, at least initially. The deadly tidal forces only develop much deeper inside, closer to the singularity. Of course, the infalling observer's fate remains sealed regardless. Once inside, the singularity lies unavoidably in their future. The time remaining before reaching the singularity for this ultra-massive black hole would be approximately several days as measured by the infalling observer's clock. Several days of fall-through, warped, space-time before encountering the region where known physics breaks down completely. During this infall, the observer would witness increasingly strange effects. Light from the outside universe, blue-shifted by the extreme gravitational field, would concentrate into a shrinking bright ring. The black hole's shadow would expand to fill most of the sky. Time dilation effects would cause external events to appear accelerated. The observer might watch the distant future of the universe play out before their eyes in the final moments before reaching the singularity. But let us step back from the event horizon and consider the black hole's broader influence on its environment. This gravitational giant doesn't exist in isolation, but sits embedded in a galaxy, likely a massive elliptical galaxy based on correlations between black hole mass and host galaxy properties. The relationship between supermassive black holes and their host galaxies represents one of the most intriguing discoveries in modern astrophysics. observations revealed tight correlations between black hole mass and various properties of the galactic bulge, the central concentration of stars. More massive bulges host more massive black holes, with the black hole mass typically representing about 0.1 to 0.2% of the bulge mass. This correlation suggests a deep connection between black hole growth and galaxy evolution, despite the black hole's gravity directly affecting only a tiny central region. The most likely explanation involves feedback processes where energy from the accreting black hole influences star formation throughout the galaxy. When the black hole actively accretes matter, the resulting radiation and jets pump enormous amounts of energy into surrounding gas. This heating prevents the gas from cooling and collapsing to form new stars. Without this feedback, galaxies would consume their gas reservoirs far more quickly, forming stars at unsustainable rates and exhausting their fuel in a cosmic instant. The feedback operates as a self-regulating cycle. Abundant cold gas feeds the black hole, triggering vigorous accretion. The resulting energy output heats and disperses the gas, shutting down both star formation and further accretion. The black hole goes quiet. Over millions of years, gas cools and accumulates again, restarting the cycle. This oscillation between active and quiescent states characterizes supermassive black hole evolution. During its active quasar phase, which we're observing, TON 618 profoundly influences its entire host galaxy. The jets and radiation heat gas across hundreds of thousands of light years. Star formation likely occurs only in protected pockets, where gas can shield itself from the black hole's fury. The galaxy's appearance would be dominated by the brilliant central quasar, outshining the combined light of all its stars. But in the present day, 10 billion years after the light we observe departed, this black hole almost certainly sits dormant. The quasar era ended billions of years ago as the universe evolved and gas supplies diminished. Today, TON 618 probably resides quietly at the centre of a massive elliptical galaxy, a sleeping giant surrounded by ancient red stars, its glory days long past. This transition from active quasar to dormant black hole represents normal evolution for these objects. In the young universe, galaxies contained abundant gas, and frequent mergers funneled material towards central black holes. Quasars blazed brilliantly among the brightest beacons in the cosmos, but as the universe aged and expanded, gas became increasingly sparse. Galaxy mergers became rarer. Most supermassive black holes exhausted their fuel supplies and faded into quiescence. Today, most galaxies host dormant supermassive black holes. Our own Sagittarius A star accretes material at a tiny fraction of its potential rate, producing only weak emission. Andromeda's central black hole shows similarly modest activity. Only a small percentage of present-day galaxies host actively accreting black holes, producing significant radiation. But occasionally, even in the modern universe, black holes reawaken. A star might wander too close and get torn apart by tidal forces in a tidal disruption event. The stellar debris forms a temporary accretion disk, causing the black hole to flare brilliantly for months or years before fading again. Or a galaxy merger might funnel fresh gas supplies toward the centre, triggering renewed activity. These temporary reawakenings give us glimpses of the black hole's power. For a time, the sleeping giant stirs, reminding us of the destructive potential lurking at every galaxy's heart. Then it settles back into dormancy, waiting for the next meal to drift within reach. The existence of such ultra-massive black holes in the early universe presents theoretical challenges. How did they grow so large so quickly? The universe was only about 3.5 billion years old when the light we observe from TON 618 departed. That might sound like ample time, but black hole growth faces limits. As mentioned earlier, the Eddington limit restricts how quickly black holes can accrete matter. Radiation pressure from the accretion process pushes back against infalling material. For continuous growth at the Eddington limit, starting from a stellar mass black hole of perhaps 100 solar masses, reaching 66 billion solar masses would require roughly 3 billion years. This calculation suggests TON 6 barely had enough time to reach its observed mass, and that's assuming continuous growth at the maximum possible rate, which seems unrealistic. In practice, accretion likely occurred in bursts separated by quiescent periods. Black holes probably spent substantial time below the Eddington limit, growing more slowly than the maximum rate. Several solutions have been proposed to this puzzle. Perhaps these ultra-massive black holes didn't start from stellar mass seeds. If the first black holes formed through direct collapse of massive gas clouds in the early universe, they might have started with masses of hundreds of thousands or even millions of solar masses, giving them a significant head start. Alternatively, the Eddington limit might not always apply strictly. Under certain conditions, particularly in the chaotic environments of early galaxies, black holes might temporarily exceed the Eddington limit through super-Eddington accretion. If the infalling material arrives from many different directions simultaneously, perhaps radiation pressure cannot halt the inflow as effectively. Another possibility involves black hole mergers. When galaxies collide, their central black holes eventually spiral together and merge, creating a single more massive black hole. If TON 618's host galaxy experienced multiple major mergers during its youth, the black hole could have grown partly through mergers rather than purely through accretion. Likely all these factors contributed: direct collapse seeds, efficient accretion taking advantage of abundant gas in the early universe, occasional super-Eddington episodes, and growth through mergers all working together to build these ultra-massive monsters in the available time. The rapid growth of supermassive black holes in the early universe connects to the broader question of how galaxies themselves formed and evolved. In the currently favoured cosmological model, structure in the universe grew hierarchically. Small fluctuations in the primordial density field, imprinted during cosmic inflation, grew over time through gravitational instability. Denser regions attracted more matter, becoming progressively denser, while less dense regions emptied out. Dark matter dominated this process initially. Being affected only by gravity and not interacting electromagnetically, dark matter could collapse freely without radiating away energy. Dark matter formed the first structures, creating gravitational potential wells into which ordinary matter subsequently fell. The first stars formed perhaps 100 to 200 million years after the Big Bang, igniting within dark matter halos containing just millions of solar masses. These population 3 stars, composed of primordial hydrogen and helium with essentially no heavier elements, were likely extremely massive, perhaps hundreds of solar masses. When they exhausted their fuel and exploded as supernovae or collapsed directly into black holes, they seeded the first black holes. Simultaneously, small galaxies began forming through the merger and accumulation of these early stellar systems. Dark matter halos collided and merged, and the baryonic matter they contained also merged, building progressively larger structures. This hierarchical assembly continues today, though the pace has slowed as cosmic expansion accelerates under dark energy's influence. By the time the universe reached an age of about 1 billion years, the first massive galaxies had assembled, and the first quasars appeared. TON 618, observed at an age of roughly 3.5 billion years, represents a somewhat later generation, but still from the era when quasars reached their peak abundance and luminosity. Understanding this cosmic history required decades of observational and theoretical work. Early telescopes could detect only the nearest, brightest objects. Distant galaxies appeared as faint smudges if visible at all. Quasars, despite their tremendous luminosity, were too distant and too compact to reveal their true nature initially. The development of spectroscopy, which analyzes light's wavelength distribution, proved crucial. By measuring redshifts, astronomers could determine distances and recognize that quasars lay at cosmological distances. By identifying spectral features, they could determine chemical compositions and physical conditions. By tracking spectral variability, They could constrain the size of emitting regions. Radio astronomy provided additional crucial insights. Many quasars emit strongly at radio wavelengths, and radio observations could resolve the jets extending for vast distances from the central engine. Very long baseline interferometry, combining signals from radio telescopes across continents, achieved angular resolution fine enough to study regions near the event horizon. X-ray astronomy revealed the hottest, most energetic emission from accretion disks. Space-based X-ray telescopes above Earth's absorbing atmosphere detected X-ray emission from distant quasars and analysed its properties, providing direct probes of material in extreme gravitational fields close to event horizons. Infrared observations penetrated the dust obscuring many active galactic nuclei, revealing objects hidden at optical wavelengths. Infrared surveys discovered heavily obscured quasars and traced star formation in quasar-host galaxies. Combining observations across the electromagnetic spectrum built a comprehensive picture of quasars as supermassive black holes surrounded by accretion disks, jets, and host galaxies, with different wavelengths probing different components and physical processes. Theoretical work proceeded in parallel, developing models of accretion disk physics, jet formation, and black hole growth. Supercomputer simulations modelled the complex interplay of gravity, gas dynamics, magnetic fields, and radiation. These simulations reproduced many observed features and made predictions tested by subsequent observations. The study of TON 618 specifically began with its identification in the Tonnant-Zintler Observatory Catalogue in 1957, but detailed characterization came much later. Early observations noted its blue colour and point-like appearance, typical of quasars, but provided little additional information. Only with modern instruments could astronomers measure its precise redshift, estimate its luminosity, and determine the central black hole's mass. Black hole mass estimates rely on several techniques. One approach uses the relationship between quasar luminosity and the Eddington limit. If we assume the quasar radiates at or near the Eddington luminosity, we can calculate the black hole mass required to produce that luminosity. This method provides rough estimates, but carries significant uncertainty because we don't know exactly what fraction of the Eddington limit applies. More reliable estimates come from analysing emission lines in quasar spectra. Broad emission lines, produced by gas moving at thousands of kilometers per second near the black hole, encode information about the velocity field. By measuring line widths and applying the virial theorem, which relates velocity dispersion to gravitational potential, astronomers can estimate the black hole mass. This reverberation mapping technique achieves even better accuracy. It exploits the time delay between variations in the central continuum emission and corresponding variations in emission line strength. This delay tells us the light travel time from the central source to the emitting gas, giving us the size of the broadline region. Combined with velocity measurements, this yields a black hole mass estimate with roughly 30% uncertainty. For TON 618, these various techniques converge on a black hole mass of approximately 66 billion solar masses, though some estimates range from 40 to 100 billion depending on assumptions and methods. Regardless of the precise value, it clearly ranks among the most massive black holes ever discovered, exceeded by only a handful of other candidates. The discovery of ultramassive black holes like TON 618 forced revisions to theories of black hole growth and galaxy formation. These objects push against theoretical limits for how much mass can accumulate within available time. They serve as extreme laboratories, testing our understanding of accretion physics, black hole formation, and cosmic structure evolution. They also represent time capsules from the early universe. The light we observe departed when the cosmos was young and different. By studying distant quasars, we learn about conditions in the young universe, about the chemical composition of early galaxies, about the properties of the intergalactic medium through which their light travelled. As quasar light journeys toward us across billions of light years, it passes through intervening gas clouds. These clouds absorb light at specific wavelengths corresponding to the atoms they contain, imprinting absorption lines on the quasar spectrum. By analysing these absorption features, astronomers can study the distribution and evolution of matter between us and the quasar, creating a three-dimensional map of cosmic structure along the line of sight. This technique, using quasars as background lights illuminating foreground material, has revealed the cosmic web's filamentary structure. Gas preferentially accumulates along filaments connecting galaxy clusters, leaving vast voids nearly empty. The absorption line studies trace this structure across cosmic time, showing how it evolved as the universe expanded and structure grew under gravity's influence. TON 618's tremendous luminosity makes it an excellent background source for such studies. Its light passes through billions of light-years of cosmic structure, encountering numerous gas clouds, each leaving its signature on the spectrum. Analysing this light provides insights not just about the quasar itself, but about everything between it and us. The study of quasars also informs our understanding of supermassive black hole demographics. How many black holes of different masses exist? How does the population evolve over cosmic time? These questions connect to broader issues about galaxy formation and evolution. Surveys have discovered thousands of quasars, enabling statistical studies of their properties. The quasar luminosity function describes how many quasars of each luminosity exist at different cosmic epochs. This function peaks at a redshift of about 2 to 3, corresponding to when the universe was roughly 2 to 3 billion years old, then declines at both earlier and later times. This peak represents the quasar era, when supermassive black holes grew most rapidly and shone most brightly. Before this era, the universe was too young for massive black holes to have formed. After this era, gas supplies diminished and quasar activity declined. We live in a relatively quiet era, long after the peak of quasar activity, when most supermassive black holes sit dormant in galaxy centres. TON 6018, observed at redshift approximately 2.2, lies near this peak era. It represents quasars at their most common and most active, when conditions favoured rapid black hole growth. Understanding objects like TON 618 helps us understand the population as a whole. The distances involved in observing TON 618 challenge comprehension. 10 billion light-years means the light has travelled for 10 billion years, covering a distance of about 10 billion light-years as measured in the current universe. But due to cosmic expansion, the object's current distance exceeds 10 billion light-years. The quasar has moved farther away during the time its light travelled toward us. In an expanding universe, distances have multiple definitions. Light travel distance measures how far light has travelled, giving the look-back time. Co-moving distance accounts for expansion, measuring the current separation. Proper distance measures the instantaneous distance at a specific cosmic time. For distant objects, these different distance measures can differ by factors of 2 or more. For TON 618 at redshift 2.2, the light travel time is approximately 10.6 billion years, meaning we observe it as it was 10.6 billion years ago. But the current co-moving distance is approximately 18.2 billion light-years due to cosmic expansion during the light travel time. The object has receded to nearly twice the light travel distance. This expansion affects observations in multiple ways. Light stretches as space expands, increasing wavelengths and decreasing photon energies. This cosmological redshift shifts entire spectra toward longer wavelengths, with far ultraviolet light becoming optical, optical becoming infrared, and so on. Correcting for this redshift requires understanding the universe's expansion history. The expansion also dims objects by multiple factors. Photons arrive less frequently because they're stretched out over time. Each photon carries less energy due to wavelength stretching. The object's apparent size increases, spreading light over larger angular area. Combined, these effects make distant objects appear much dimmer than they would at the same distance in a non-expanding universe. Despite these dimming effects, TON 618 remains visible and bright across cosmic distances, testifying to its tremendous intrinsic luminosity. An object radiating 140 trillion times, the Sun's luminosity can overcome even cosmological dimming to remain detectable at 10 billion light-years. As we hover here near the accretion disk, observing this cosmic monster from what in human terms would be a safe distance, but remains unfathomably close in cosmic terms, we must remember this represents the universe at less than 1/4 of its current age. This is ancient history, frozen in light now reaching us after billions of years of travel. In the current moment, in real time, this object exists 10.6 billion years older than what we observe. Stars that were forming when this light departed have long since died. Gas clouds have evolved, merged, dispersed. The galaxy itself has likely merged with other galaxies multiple times, transforming into a massive elliptical system. The quasar has almost certainly shut down, its fuel exhausted, leaving only the dark, silent black hole at the centre. We cannot know TON 618's current state without waiting another 10.6 billion years for light emitted today to reach us. We're forever locked into observing its past, seeing it as it was in the universe's youth, unable to know its present condition. This limitation applies to all distant objects. The farther we look in space, the farther we look back in time. This fundamental limitation, that observation equals looking backward through time, transforms astronomy into a form of cosmic archaeology. We excavate the past not by digging through layers of rock, but by gathering ancient light. Every observation becomes a window into history, revealing not what is, but what was. For TON 618, this means we observe a snapshot from 10.6 billion years ago, frozen in the light now reaching our telescopes. We see the black hole as it existed when actively feeding, when jets blasted outward at relativistic speeds, when the accretion disk blazed brilliantly enough to outshine hundreds of billions of stars. We cannot know if this activity continues today or ceased billions of years ago. This temporal disconnect between observation and reality pervades cosmology. When we look at the Andromeda Galaxy, we see it as it was 2.5 million years ago. When we observe galaxies in the Virgo cluster, we see them as they existed roughly 50 million years ago. The farther we look, the deeper into the past we peer, until at the greatest distances we observe galaxies as they appeared when the universe was only a few hundred million years old. This creates an unusual situation, where our knowledge of the universe's past potentially exceeds our knowledge of its present. We possess detailed observations of the early universe through cosmic microwave background radiation, observations of galaxy formation at high redshift, records of the universe at various evolutionary stages. But the current state of distant galaxies remains unknown, hidden from us by the finite speed of light. Let us now examine the black hole itself more closely, approaching the event horizon and considering what lies within. General relativity provides equations describing black hole geometry, but their solutions reveal physics stranger than almost anything else in nature. A non-rotating, uncharged black hole is described by the Schwarzschild solution, found by Karl Schwarzschild in 1915, mere months after Einstein published general relativity. This solution reveals that black holes have no hair, meaning they're characterized completely by just three properties: mass, electric charge, and angular momentum. All other information about the material that formed them or fell into them is lost. This no-hair theorem, proven rigorously in the 1970s, states that regardless of what falls into a black hole, whether hydrogen, iron, antimatter, or exotic particles, the resulting black hole depends only on total mass, charge, and spin. All detailed information about composition, structure, and history vanishes beyond the event horizon, hidden from external observation. For TON 618, which formed through complex astrophysical processes involving countless stars, gas clouds, and possibly other black holes, This means the black hole retains no memory of its formation history beyond these three numbers. It has no internal structure visible from outside, no features distinguishing material that fell in yesterday from material that fell in billions of years ago. The event horizon itself represents a boundary in space-time where the escape velocity equals the speed of light. Inside this boundary, all time-like and light-like paths lead inexorably toward the singularity at the centre. Outside, escape remains possible. The horizon marks the boundary between these regions. For a Schwarzschild black hole, the horizon radius, called the Schwarzschild radius, is given by a simple formula: 2 times the gravitational constant times the mass divided by the speed of light squared. For Ton 618's mass of 66 billion solar masses, this yields approximately 195 billion kilometers, or about 1,300 astronomical units. To visualize this scale, if you could place this black hole at the Sun's position, its event horizon would extend beyond Neptune's orbit, beyond the Kuiper belt where Pluto orbits, reaching into the inner Oort cloud. The entire planetary system, all the planets that took billions of years to form through slow accumulation of dust and rock, would lie trapped inside the event horizon's inescapable grasp. But Ton 618 almost certainly rotates. Black holes formed through realistic astrophysical processes inevitably possess angular momentum. Material falling into the black hole carries angular momentum inward, spinning up the black hole. Accreting material almost always possesses net rotation in one direction, causing the black hole to spin faster over time. Rotating black holes are described by the Kerr solution, discovered by Roy Kerr in 1963. This solution is considerably more complex than Schwarzschild, introducing features like the ergosphere and frame dragging. The event horizon for a Kerr black hole is slightly smaller than for a Schwarzschild black hole of equal mass, and its shape is oblate, slightly flattened at the poles. The maximum possible rotation rate occurs when the black hole spins at the speed of light at its equator. At this extremal limit, the event horizon radius shrinks to half the Schwarzschild value. For Ton 618, if rotating at the maximum rate, the event horizon radius would be approximately 650 astronomical units, still enormous but only half the non-rotating value. Observations suggest many supermassive black holes rotate rapidly, perhaps near the extremal limit. The efficiency of converting and falling matter into radiation depends on rotation rate. Non-rotating black holes can convert at most about 6% of infalling mass into radiated energy. Maximally rotating black holes can achieve efficiencies approaching 42%. The tremendous luminosity of quasars suggests their central black holes likely rotate rapidly. The ergosphere, unique to rotating black holes, extends outside the event horizon. Within this region, space-time itself is dragged around the black hole, and nothing can remain stationary relative to distant observers. Even light must rotate with the black hole. This frame-dragging effect becomes stronger closer to the horizon, and more pronounced for rapidly rotating black holes. Theoretically, the ergosphere enables the Penrose process, proposed by Roger Penrose in 1969. If a particle enters the ergosphere and splits into 2 particles, with one falling into the black hole and the other escaping, the escaping particle can carry away more energy than the original particle possessed. The extra energy comes from the black hole's rotational energy, slowing its spin. This process could theoretically extract up to 29% of a black hole's mass energy. Whether the Penrose process actually occurs in nature remains uncertain. It requires precise conditions unlikely to be common, but it demonstrates that rotating black holes store enormous amounts of extractable energy in their rotation, potentially accessible through sufficiently advanced technology. A civilization capable of exploiting this process could power itself by harvesting energy from rotating black holes. The jets observed emerging from many active galactic nuclei, including likely from Ton 618, may be powered partly by extracting rotational energy through magnetic field interactions, a mechanism called the Blandford-Znajek process. Magnetic field lines threading through the ergosphere and anchored in the accretion disk can tap the black hole's rotation, accelerating particles to relativistic speeds and launching them outward as jets. As we approach even closer to the event horizon, we must consider what happens to infalling matter. Material doesn't simply disappear at the horizon, but continues existing inside, falling toward the singularity. The journey from horizon to singularity takes a finite amount of proper time as measured by an infalling clock. For this ultramassive black hole, the fall time is surprisingly long. An observer falling radially from the event horizon to the singularity would experience approximately several days of proper time during the fall. This contrasts sharply with stellar mass black holes, where the fall time is mere milliseconds. The larger the black hole, the longer the internal fall time. During this fall, the observer would witness increasingly extreme tidal forces. Although gentle at the horizon for an ultramassive black hole, tidal forces grow rapidly, moving inward. The gravitational gradient, the difference in gravitational pull across an extended object, increases dramatically. Eventually, these tidal forces exceed any material strength. Molecular bonds break, atomic structures deform, even atomic nuclei would be torn apart if they survived long enough. This spaghettification becomes extreme as the singularity approaches, stretching matter into ever thinner strands aligned radially with the gravitational field. The singularity itself represents a breakdown of general relativity. At this point, space-time curvature becomes infinite, densities become infinite, and the equations produce meaningless results. General relativity predicts its own failure, indicating the need for a deeper theory incorporating quantum mechanics. What actually happens at the singularity remains one of physics' greatest mysteries. Does space-time truly become infinite in curvature, or do quantum gravity effects become important first, preventing actual infinities? Does the singularity have structure, or is it a true geometric point? These questions await a complete theory of quantum gravity to answer. Several candidate theories attempt to unify quantum mechanics and general relativity. String theory proposes that fundamental particles are actually tiny vibrating strings, with different vibration modes corresponding to different particles. In string theory, black hole singularities might be replaced by extended objects, avoiding true infinities. Loop quantum gravity takes a different approach, suggesting space-time itself has discrete structure at the smallest scales, like pixels in an image. In this framework, singularities might be replaced by quantum bounces, where collapsing matter reaches a minimum size then rebounds, potentially creating new universe regions. These theories remain highly speculative and unproven. We lack experimental access to quantum gravity regimes. The energies and densities required to test these theories directly exceed anything achievable with current or foreseeable technology. Black hole interiors represent nature's only laboratories where quantum gravity becomes relevant, but they're hidden behind event horizons, inaccessible to observation. This inaccessibility raises profound questions about the nature of scientific knowledge. If we can never observe black hole interiors, can we truly claim to understand them? Science relies on observation and experiment to test theories. Without empirical access, how can we distinguish correct theories from incorrect ones? One approach involves indirect tests. While we cannot observe singularities directly, we can study black hole exteriors and test whether observations match theoretical predictions. If a theory correctly predicts everything we can observe, perhaps we can trust its predictions about what we cannot observe. Another approach seeks signatures of quantum gravity and observable effects. Perhaps Hawking radiation, though incredibly weak, carries subtle imprints of quantum gravity effect occurring near the singularity. Or perhaps gravitational waves from black hole mergers encode information about black hole interiors in ways not yet recognized. The information paradox mentioned earlier also connects to these questions. If information falling into black holes is truly lost, this violates quantum mechanics' fundamental principles. But if information is preserved, it must escape somehow, presumably through Hawking radiation. Understanding how this occurs likely requires understanding quantum gravity. Recent developments suggest information may be preserved through subtle quantum correlations between infalling matter and outgoing radiation. These correlations, too weak to observe practically, might theoretically enable information reconstruction from Hawking radiation, resolving the paradox while preserving both quantum mechanics and general relativity. Stephen Hawking, who originally proposed information loss, later conceded information might be preserved, though debates continue about the mechanism. The question remains actively researched, with new proposals and calculations appearing regularly. Black holes, seemingly simple objects characterized by just 3 numbers, continue revealing unexpected theoretical depth. Let us now pull back from the event horizon and consider TON 618's place in the broader population of black holes. Across the universe, black holes span an enormous mass, range from a few solar masses for stellar remnants to tens of billions of solar masses for the most extreme supermassive examples. Stellar mass black holes form from massive stars. When a star exceeding roughly 20 to 25 solar masses exhausts its nuclear fuel, no force can support its core against gravitational collapse. The core implodes, forming a black hole while the outer layers explode as a supernova. These stellar mass black holes typically range from 5 to perhaps 100 solar masses. Intermediate mass black holes, if they exist, would fill the gap between stellar and supermassive black holes, ranging from hundreds to hundreds of thousands of solar masses. Evidence for this population remains tentative. Some ultraluminous X-ray sources might be intermediate mass black holes accreting matter, and some globular clusters might harbour them, but definitive detections remain elusive. Supermassive black holes ranging from millions to billions of solar masses reside in most galaxy centres. How they formed remains debated. Stellar mass black holes can merge and grow, but reaching supermassive scales this way requires immense time. Direct collapse of massive gas clouds in the early universe might create intermediate mass seeds, which then grew to supermassive scales through accretion and mergers. TON 618, with 66 billion solar masses, represents the ultramassive extreme of the supermassive population. Only a handful of known black holes rival or exceed its mass. These ultramassive black holes challenge formation theories, pushing against time constraints for how quickly black holes can grow in the available cosmic history. The distribution of black hole masses provides clues about formation mechanisms. If we plot the number of black holes versus mass, we see distinct populations. Stellar mass black holes cluster around 10 solar masses. Supermassive black holes show a broad distribution peaking around 100 million solar masses. The gap between suggests different formation mechanisms. Gravitational wave detections by LIGO, Virgo and Kagra observatories have revolutionized black hole studies. These detectors observe ripples in space-time produced by merging black holes. Since beginning operations in 2015, they've detected dozens of stellar mass black hole mergers, revealing unexpected properties of the stellar mass population. Many detected black holes are more massive than predicted by stellar evolution theory. Some mergers involve black holes of 30, 50 or even 85 solar masses, larger than expected from stellar collapse. These detections suggest gaps in our understanding of massive star evolution or hint at alternative formation mechanisms. Gravitational wave astronomy also enables tests of general relativity in extreme conditions. Black hole mergers involve space-time curvature at its most intense, with velocities approaching light speed and gravitational fields near the maximum possible strength. Observed waveforms match general relativities, predictions remarkably well, providing strong empirical support for the theory. Future gravitational wave detectors will observe supermassive black hole mergers. The Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will detect gravitational waves at much lower frequencies than ground-based detectors, accessing signals from mergers of black holes with millions to billions of solar masses. When two galaxies merge, their central supermassive black holes eventually spiral together through dynamical friction, forming a binary system. This binary gradually shrinks through gravitational wave emission and interactions with surrounding stars and gas. Eventually the black holes merge, producing a tremendous burst of gravitational waves and creating a single more massive black hole. TON 618 might have formed partly through such mergers. Each merger adds mass and releases energy, potentially explaining how it reached such extreme mass so quickly. Future LISA observations will detect similar mergers occurring in the present-day universe, revealing how often supermassive black hole mergers occur and how they affect host galaxies. The merger of two supermassive black holes represents one of the most energetic events possible in the universe. In the final moments before coalescence, the black holes orbit each other thousands of times per second, releasing more power in gravitational waves than all the stars in the observable universe emit in light combined. This stupendous energy output lasts only fractions of a second, but during that brief interval, the merging black holes become the brightest sources of gravitational radiation in the cosmos. The resulting gravitational waves carry information about the merging black holes' masses, spins, and orbital parameters. By analysing the waveform's evolution, astronomers can reconstruct the merger's dynamics, determining how the black holes spiraled together, how they collided, and how the remnant black hole settled into its final state through a process called ring down, where it emits gravitational waves at characteristic frequencies as it sheds irregularities. These observations will test general relativity's predictions about black hole mergers with unprecedented precision. General relativity makes specific predictions about waveform shapes, ring-down frequencies, and the final black hole's properties. Any deviations would indicate new physics, perhaps modifications to general relativity needed at extreme energies, or evidence for exotic physics in black hole environments. The merger also potentially affects the surrounding galaxy. The gravitational wave recoil, caused by asymmetric emission of gravitational radiation, can kick the merged black hole in a specific direction at speeds potentially reaching thousands of kilometers per second. For typical mergers, the recoil is modest, perhaps tens to hundreds of kilometers per second. But certain spin configurations can produce kicks exceeding 4,000 kilometers per second, sufficient to eject the black hole entirely from its host galaxy. Such ejected black holes would become intergalactic wanderers, carrying their immediate stellar neighbourhoods with them, but divorced from their parent galaxies. Astronomers have searched for evidence of recoiling black holes, finding some candidates showing offset positions or unusual velocity shifts, though definitive identifications remain challenging. For TON 618, if its mass accumulated partly through mergers, each merger would have produced gravitational recoil. The cumulative effect of multiple kicks could have displaced the black hole significantly from the galaxy's centre, though over time dynamical friction would drag it back toward the centre. The black hole's current position likely reflects a balance between merger kicks and dynamical friction. Beyond mergers, supermassive black holes influence their environments through multiple mechanisms. We've discussed feedback from jets and radiation heating surrounding gas. But black holes also affect stellar dynamics in their immediate vicinity, creating distinct regions with different properties. Very close to the black hole, within about 0.01 parsecs for a black hole of this mass, lies the sphere of influence, where the black hole's gravity dominates stellar motions. Stars in this region orbit the black hole directly rather than participating in the galaxy's overall rotation. Their orbital velocities reflect the black hole's mass, enabling dynamicists to measure black hole masses by observing stellar motions. This technique has been applied most successfully to our galaxy's central black hole, Sagittarius A star. Decades of observations tracking individual stars' motions around the galactic centre have revealed orbital periods, velocities, and trajectories. These measurements enabled precise determination of the black hole's mass and provided tests of general relativity in the strong field regime near the black hole. One star, designated S2, orbits Sagittarius A star with a period of about 16 years, approaching within about 17 light hours at closest approach. Observations of S2's orbit showed gravitational redshift and relativistic precession, effects predicted by general relativity but never before observed so clearly around a supermassive black hole. These observations earned the 2020 Nobel Prize in Physics. For TON 618, the sphere of influence extends much larger due to its enormous mass, perhaps several parsecs in radius. Thousands or millions of stars orbit within this region, their motions governed primarily by the black hole's gravity. If we could observe individual stars' motions around TON 618, we could measure its mass even more precisely than current spectroscopic methods allow. Unfortunately, TON 618's tremendous distance makes resolving individual stars impossible with current technology. The entire galaxy appears as an extended smudge, with no chance of tracking individual stellar orbits. This limitation applies to all distant supermassive black holes. Only for the nearest galaxies can we resolve stars well enough to measure black hole masses dynamically. Moving outward from the sphere of influence, we encounter regions where stellar densities become extreme. Near supermassive black holes, gravitational focusing concentrates stars into dense clusters. In the Milky Way's galactic center, stellar densities reach millions of stars per cubic parsec, far exceeding the few stars per cubic parsec typical of the galactic disk. These high densities create unusual conditions. Stars frequently pass close to each other, experiencing gravitational perturbations that alter their orbits. Close encounters can eject stars from the galactic center at high velocities, creating hypervelocity stars traveling fast enough to escape the galaxy entirely. Dozens of hypervelocity stars have been discovered in the Milky Way's halo, likely ejected from the galactic center through interactions involving the central black hole. The dense stellar environment also facilitates tidal disruption events. When a star passes within the black hole's tidal radius, where tidal forces exceed the star's self-gravity, the star gets torn apart. The stellar debris forms a temporary accretion disk, producing a bright flare as material falls into the black hole. Tidal disruption events occur roughly once every 10,000 to 100,000 years per galaxy. For a typical galaxy harboring a supermassive black hole, this represents rare but spectacular displays of the black hole's destructive power. The flare can outshine the entire host galaxy for weeks or months before fading as the debris disk dissipates. Observatories have detected dozens of tidal disruption events in distant galaxies, recognizing them by their characteristic luminosity evolution and spectral properties. These events provide unique opportunities to study black holes in otherwise quiescent galaxies and probe the physics of accretion disk formation. For TON 618, actively accreting in its quasar phase, tidal disruption events would be relatively insignificant, adding negligibly to the already enormous accretion rate. But in its current dormant state, billions of years after the light we observed departed, tidal disruption events might represent its primary activity, briefly illuminating the black hole when an unlucky star wanders too close. The stellar population near supermassive black holes also includes exotic objects rarely found elsewhere. The extreme environment near the black hole potentially hosts unusual stellar types, including stars in very tight binary systems, compact objects like neutron stars and stellar mass black holes, and possibly even planets stripped from their parent stars by gravitational interactions. Some theories suggest intermediate mass black holes might sink to galaxy centers through dynamical friction, orbiting the central supermassive black hole before eventually merging with it. If present, these intermediate mass black holes would create complex dynamical systems, potentially ejecting stars and producing distinctive gravitational wave signals. the galactic center environment also experiences intense radiation from the quasar during active phases. This radiation ionizes surrounding gas, heats material to extreme temperatures, and potentially affects star formation in the inner galaxy. Stars forming in such harsh environments might have unusual properties, perhaps lacking planets due to radiation stripping away protoplanetary disks. Let us now consider TON 618's role in cosmic structure formation more broadly. Supermassive black holes don't exist in isolation but are embedded in the cosmic web, the large-scale structure of the universe. Understanding their formation and evolution requires understanding how galaxies themselves formed and evolved within this structure. The cosmic web emerged from tiny quantum fluctuations during cosmic inflation, stretched to macroscopic scales by exponential expansion in the universe's first instance. These fluctuations created slight density variations in the primordial plasma, regions slightly denser or less dense than average. After inflation ended and the universe began its standard expansion, these density variations evolved under gravity. Denser regions attracted more matter, becoming progressively denser. Less dense regions lost matter to their denser neighbours, becoming progressively more empty. This gravitational instability amplified initial tiny perturbations into the cosmic web's current structure over billions of years. Dark matter, unaffected by radiation pressure and electromagnetic interactions, collapsed first. By the time the universe became transparent about 380,000 years after the Big Bang, dark matter had already begun forming structures. Ordinary matter, initially prevented from collapsing by radiation pressure, fell into the gravitational potential wells created by dark matter after recombination freed it from radiation's influence. The first stars ignited within dark matter halos containing millions of solar masses, perhaps 100 to 200 million years after the Big Bang. These population 3 stars, composed of primordial hydrogen and helium without heavier elements, were likely extremely massive, perhaps hundreds of solar masses. They burned brilliantly but briefly, exhausting their fuel in mere millions of years before exploding as supernovae or collapsing into black holes. These first black holes, perhaps tens to hundreds of solar masses, seeded the growth of supermassive black holes. Through accretion and mergers, they grew to millions, then billions of solar masses over hundreds of millions of years. Simultaneously, the first galaxies assembled through hierarchical merging of smaller systems, with black hole growth and galaxy growth proceeding in tandem. By approximately 1 billion years after the Big Bang, the first quasars appeared, indicating that supermassive black holes containing billions of solar masses had already formed. The rapidity of this growth presents theoretical challenges, as discussed earlier, requiring efficient accretion or alternative formation mechanisms like direct collapse. TON 618, observed at approximately 3.5 billion years after the Big Bang, represents a somewhat later generation of quasars, from the peak era of quasar activity, when supermassive black holes shone most brilliantly. Understanding how it grew so massive so quickly requires understanding the interplay of multiple processes: direct collapse seeds, efficient accretion, merger-driven growth, and feedback effects. The quasar era, peaking at redshifts around 2 to 3, corresponds to when galaxies underwent their most active star formation and most vigorous black hole growth. Conditions in the young universe favoured these processes. Gas was more abundant, galaxy mergers were more frequent, and the intergalactic medium was denser. These factors combined to fuel both star formation and black hole accretion at rates far exceeding those in the present-day universe. As the universe aged and expanded, conditions changed. The gas supply diminished as material became locked in stars and stellar remnants. Galaxy mergers became less frequent as cosmic expansion accelerated and galaxy groups spread apart. The intergalactic medium became more diffuse. These changes caused both star formation rates and black hole accretion rates to decline substantially. Today, most star formation occurs in spiral galaxies like the Milky Way. where cold gas continues collapsing galactic disks, but the rate is modest compared to the frenzied star formation in the young universe. Similarly, most supermassive black holes sit quiescent, accreting minimal amounts of material, with only a small percentage showing significant activity. This evolution from active to passive characterizes cosmic history. The universe has calmed substantially since its violent youth. The quasar era, when objects like TON 618 blazed brilliantly, has long since ended. We live in a relatively quiet era, long after the peak of cosmic activity. But this quiescence will not last forever. Current observations indicate the universe's expansion is accelerating under the influence of dark energy, a mysterious component comprising about 70% of the universe's total energy density. This acceleration will continue increasing, ultimately dominating over matter's gravitational attraction. In the far future, dark energy's effects will become progressively more extreme. Galaxy clusters will disperse as expansion pulls galaxies apart faster than gravity can hold them together. Eventually, even galaxies themselves might be torn apart by accelerating expansion in a scenario called the Big Rip, though this depends on dark energy's precise properties. But long before any such catastrophic ending, the universe will undergo dramatic changes. Star formation will continue for tens to hundreds of billions of years, but eventually all available gas will be consumed or dispersed. Once gas supplies are exhausted, no new stars can form. The era of star formation, which began shortly after the Big Bang and continues today, will eventually end. After star formation ceases, existing stars will continue burning until they exhaust their fuel. Low-mass stars, the red dwarfs that make up the majority of stars, burn slowly and can shine for trillions of years, but eventually, even these miserly burners will exhaust their fuel, cooling into white dwarfs, compact stellar remnants supported by electron degeneracy pressure. Massive stars will continue exploding as supernovae, creating neutron stars and black holes. White dwarfs will accumulate, slowly cooling over trillions of years. Eventually, perhaps 100 trillion years from now, the last star will fade. The stelliferous era, the age of stars, will end. The universe will enter the degenerate era, dominated by white dwarfs, neutron stars and black holes, with no new stars forming. During this degenerate era, galaxies will gradually evaporate. Close gravitational encounters between stars and compact objects will occasionally give objects enough energy to escape the galaxy, carrying off mass and energy. Over immensely long timescales, perhaps 1019 to 1020 years, galaxies will disperse, leaving only isolated stellar remnants and black holes drifting through an expanding, cooling universe. Supermassive black holes like TON 618 will remain, slowly growing through occasional captures of wandering stellar remnants and evaporating through Hawking radiation. For an ultramassive black hole, Hawking radiation is incredibly weak, making evaporation times almost incomprehensibly long. The evaporation time for a black hole scales as the cube of its mass. For a stellar mass black hole of 10 solar masses, complete evaporation takes approximately 1067 years. For TON 618 with 66 billion solar masses, the evaporation time reaches approximately 100 years, far exceeding the current age of the universe repeated countless times. During this vast time span, the black hole will slowly radiate away its mass as Hawking radiation. The temperature of this radiation is inversely proportional to mass, so as the black hole shrinks, it grows hotter. Initially, Hawking radiation is utterly negligible, far colder than the cosmic microwave background. But as the black hole shrinks, the radiation intensifies. In the final stages, when the black hole is evaporated down to perhaps stellar mass or smaller, Hawking radiation becomes intense. The black hole shines brilliantly, radiating away its remaining mass in a final burst, lasting perhaps minutes to hours depending on details. Then it disappears completely, leaving only radiation dispersing into the void. This process will play out for every black hole in the universe. Stellar mass black holes will evaporate first, followed by intermediate mass black holes if they exist, then supermassive black holes, and finally the ultramassive monsters like TON 618 will be among the very last objects to disappear. After all black holes evaporate, the black hole era ends. The universe enters what has been termed the dark era, containing only radiation and perhaps some exotic particles. Protons themselves might decay on timescales of perhaps 10 to 34 years if certain theories of particle physics are correct, though this remains unproven. If protons decay, even the white dwarfs and neutron stars remaining from the degenerate era will gradually dissolve into radiation. Eventually, the universe approaches maximum entropy, a state of thermal equilibrium where no useful energy differences remain. No structure, no complexity, no possibility of life or consciousness, just radiation and possibly exotic particles expanding forever in an increasingly cold, dark and empty universe. This far future scenario, extrapolated from current physics understanding, paints a bleak picture, yet it remains speculative. We don't know dark energy's ultimate fate. We don't know if protons decay. We don't know if Hawking radiation truly evaporates black holes as predicted. Unknown physics might intervene at any point. And even if this scenario unfolds as predicted, quantum fluctuations in the far future might spontaneously create new universes through quantum tunneling, possibly with different physical laws. The ultimate fate of existence remains profoundly uncertain. But for now, in this era of stars and galaxies, of structure and complexity, objects like TON 618 represent the universe's capacity for extremes. They demonstrate that nature can create phenomena far exceeding human intuition, objects that challenge our understanding and push our theories to their limits. Studying these extreme objects advances our knowledge. Each observation of a distant quasar, each measurement of a black hole's mass, each detection of a gravitational wave from a black hole merger adds to our understanding of how the universe works. We build theoretical frameworks, test them against observations, refine our models, and gradually approach deeper comprehension. This process exemplifies the scientific method. We observe phenomena, formulate hypotheses to explain them, make predictions, test those predictions through further observations, and revise our theories as needed. Through this iterative process, we've developed remarkably successful theories like general relativity and quantum mechanics, theories that describe nature's behaviour with extraordinary accuracy. Yet, gaps remain. General relativity and quantum mechanics, our two most fundamental theories, are mutually incompatible at the deepest level. They make different predictions about what happens at black hole singularities, at the Big Bang, wherever quantum gravity effects become important. Reconciling these theories into a unified framework remains one of physics' greatest challenges. Black holes provide crucial laboratories for testing quantum gravity theories, despite being observationally inaccessible beyond their event horizons. The information paradox, Hawking radiation, and singularity physics all require quantum gravity for complete understanding. As we develop candidate theories like string theory, loop quantum gravity and others, black holes provide testing grounds for their predictions. TON 618, as one of the most extreme black holes known, pushes these theories to their limits. Its tremendous mass, ancient formation epoch, and ultraluminous quasar phase make it exceptional even among supermassive black holes. Understanding how such objects formed and evolved constrains theories of structure formation, black hole growth, and galaxy evolution. Future observations will reveal more about TON 618 and similar objects. Next-generation telescopes like the James Webb Space Telescope, the Extremely Large Telescope, and others will observe distant quasars with unprecedented sensitivity and resolution, measuring their properties more accurately and discovering new examples at even greater distances. These observations will trace supermassive black hole growth across cosmic time, revealing how the population evolved from the first black holes formed hundreds of millions of years after the Big Bang to the dormant giants occupying present-day galaxy centers. Statistical studies of large samples will reveal formation mechanisms, growth rates, and relationships between black holes and their host galaxies. Gravitational wave astronomy will complement electromagnetic observations. LISA will detect supermassive black hole mergers, revealing merger rates and providing independent black hole mass measurements. Pulsar timing arrays, which monitor millisecond pulses for gravitational wave-induced timing variations, might detect the background gravitational wave signal from all supermassive black hole mergers throughout cosmic history. These diverse observational approaches, combined with advancing theoretical understanding and increasingly sophisticated computer simulations, will deepen our comprehension of supermassive black holes and their role in cosmic evolution. We'll learn how galaxies and black holes co-evolved, how feedback processes regulated their growth, and how the universe transitioned from the violent quasar era to the relatively quiet present. But beyond scientific knowledge, studying objects like TON 618 serves another purpose. It reminds us of our place in the cosmos, of the vast scales and tremendous energies operating in nature, of the universe's profound strangeness and beauty. When we contemplate a black hole containing 66 billion solar masses, shining with the luminosity of 140 trillion suns, existing 10 billion light-years distant, we confront scales that dissolve meaning from human intuition. Our brains evolve to understand the immediate environment, to navigate terrestrial scales and human time scales. Cosmic scales overwhelm these intuitions, yet through mathematics and physics, through careful observation and logical reasoning, we can understand these phenomena. We can calculate the event horizon's size, predict Hawking radiation's temperature, model accretion disk dynamics. We extend our understanding far beyond direct experience through the power of abstract thought. This represents a remarkable achievement. Curious creatures on a small world orbiting an ordinary star in an average galaxy have developed the capability to comprehend phenomena occurring billions of light-years away, to understand the physics of objects we'll never visit, to predict events we'll never witness. This comprehension brings responsibility. As we learn about the universe, we recognize both our significance and our insignificance. Significant in that we represent, as far as we know, the universe's means of understanding itself. Conscious beings capable of contemplating existence. Insignificant in that we occupy a tiny corner of a vast cosmos that would proceed unchanged without us. This dual perspective, recognizing both importance and unimportance, can inform how we approach existence. We matter to ourselves and to each other, but the universe offers no inherent meaning. We must create our own meaning through our choices and actions. Studying the universe provides one such source of meaning. The quest to understand existence, to reveal nature's secrets, to expand human knowledge represents a noble endeavour. Each discovery, each insight, each advancement adds to humanity's collective understanding and enriches our species' story. TON 618, then, is more than merely an ultramassive black hole 10 billion light-years away. It's a challenge to our understanding, a testing ground for our theories, a window into cosmic history, and a reminder of the universe's grandeur. It embodies the scientific enterprise's spirit, the drive to explore and comprehend despite overwhelming scales and daunting challenges. Our journey ends here, at the edge of the observable universe, having travelled impossible distances to witness an impossible object. We've gazed upon a black hole that should not exist according to our initial understanding, forced revisions to our theories, and emerged with deeper comprehension. The singularity awaits at the centre, hidden forever behind the event horizon, perhaps concealing physics beyond current knowledge. We cannot observe it, cannot visit it, cannot know with certainty what lies within. yet we've learned enough to know we're missing something fundamental, that deeper truths await discovery. This recognition of our ignorance paradoxically demonstrates our progress. We've advanced far enough to recognize the boundaries of our knowledge, to identify where our theories break down, to pose questions we cannot yet answer. This represents not failure, but opportunity, pointing toward future discoveries. The story of TON 618, of supermassive black holes, of quasars and galaxies and cosmic structure, continues unfolding. New observations arrive constantly, theories evolve, understanding deepens. The scientific quest continues because there's always more to learn, always deeper questions to ask, always new mysteries emerging from solved ones. And in this endless pursuit of knowledge, we find purpose, not handed down from the cosmos, but created through our curiosity, sustained through our determination, fulfilled through our discoveries. We are the universe contemplating itself, and in that contemplation, we find meaning. This is TON 618. This is the story of the ultramassive black hole at the edge of cosmic possibility. This is what we've learned, what we've discovered, what we've understood through decades of observation and theory. And this is merely the beginning, for the universe holds countless more secrets awaiting revelation, and the quest to understand will continue as long as curious minds persist. The journey to understanding TON 618 and objects like it spans not just cosmic distances but human history. For most of our existence as a species, we possess no knowledge of galaxies beyond our own, no conception of black holes, no awareness that the universe extended billions of light years in every direction. The development of this understanding represents one of humanity's greatest intellectual achievements. Ancient peoples observed the night sky and created myths to explain celestial phenomena. The Milky Way's band of light inspired stories across cultures. Some saw it as a river, others as a path for souls, others as spilled milk from a goddess. These explanations, while factually incorrect, represented attempts to make sense of observations using available conceptual frameworks. The scientific revolution, beginning in the 16th and 17th centuries, introduced new methods for understanding nature. Galileo's telescope revealed Jupiter's moons, Saturn's rings, and mountains on the moon, demonstrating that celestial objects were physical places rather than perfect ethereal spheres. Newton's laws of motion and gravity provided a mathematical framework for predicting planetary motions. But even Newton's powerful insights couldn't reveal the true nature of faint nebulous patches visible through telescopes. Were these clouds within our galaxy, or separate systems entirely? The question remained unanswered for centuries, limited by observational capabilities. The breakthrough came in the 1920s when Edwin Hubble, using the 100-inch telescope at Mount Wilson Observatory, resolved individual stars in the Andromeda Nebula. By identifying Cepheid variable stars, whose pulsation periods correlate with intrinsic brightness, Hubble determined Andromeda's distance at roughly 900,000 light-years, far beyond our galaxy's boundaries. This proved Andromeda was a separate galaxy, implying the universe contained countless such systems. Hubble's subsequent work revealed another, profound truth. When he measured the spectral shifts of distant galaxies, he found they were receding from us, with more distant galaxies receding faster. This relationship, now called Hubble's law, indicated the universe itself was expanding. Extrapolating backwards suggested the universe began in an extremely dense hot state, approximately 13.8 billion years ago, an event later termed the Big Bang. These discoveries transformed our cosmic perspective. The universe went from a static collection of stars to a dynamic, evolving entity with a definite beginning and ongoing expansion. Our galaxy became one among billions, each containing billions of stars. The scales involved exploded beyond prior conception. Parallel developments in physics provided tools for understanding extreme cosmic phenomena. Einstein's general relativity, published in 1915, revolutionized our understanding of gravity as space-time curvature rather than a force. Solutions to Einstein's equations describe previously unimaginable objects like black holes, where gravity becomes so intense that space-time curves back on itself. Initially, physicists regarded black holes as mathematical curiosities rather than real objects. Einstein himself doubted their physical existence, but observations gradually revealed their presence. Strong X-ray sources in binary star systems, where matter from a companion star accretes onto a compact object, suggested stellar mass black holes. The realization that extremely compact, massive objects occupied galaxy centers led to the supermassive black hole paradigm. The discovery of quasars in the early 1960s marked another watershed moment. These incredibly luminous objects, visible across billions of light years despite appearing as points, defied explanation until theorists proposed supermassive black holes as their power source. Only the immense gravitational potential energy available from material falling into supermassive black holes could explain quasars' tremendous luminosity from such compact regions. TON 618's identification as a quasar followed this theoretical framework. Initial observations noted its unusual brightness and spectrum. Subsequent detailed studies revealed its extraordinary distance and luminosity, placing it among the most extreme quasars known. Estimates of the central black hole's mass revealed it as one of the most massive ever discovered. Each step in this journey involved contributions from countless individuals, instrument builders who constructed ever larger telescopes, observers who spent cold nights gathering photons from distant objects, theorists who developed mathematical frameworks for understanding observations, computer scientists who built simulations modelling complex astrophysical processes, all contributing pieces to the gradually emerging picture. This collaborative, cumulative nature characterises science. Individual discoveries build on prior work, each generation standing on its predecessors' shoulders. No single person discovered black holes or understood quasars. Rather, communities of scientists working over decades assembled the knowledge collectively, sharing findings, critiquing theories, refining understanding through iterative improvement. This process continues today with greater intensity than ever before. Modern telescopes dwarf their predecessors in size and sensitivity. Space-based observatories escape atmospheric interference, accessing wavelengths blocked from ground-based instruments. Gravitational wave detectors open entirely new observational windows. Supercomputers enable simulations of unprecedented sophistication. The James Webb Space Telescope, launched in 2021, exemplifies current capabilities. Its 6.5-meter mirror and infrared sensitivity enable observations of the most distant galaxies, seeing them as they appeared when the universe was only a few 100 million years old. Webb observes the first stars and galaxies forming, witnessing cosmic dawn directly. These observations reveal surprising complexity in the early universe. Galaxies appear more mature and organised than expected at such early times. Supermassive black holes exist earlier than theoretical models easily accommodate. The data force refinements to formation theories, suggesting we're still missing pieces of the puzzle. Ground-based telescopes also continue advancing. The extremely large telescope, currently under construction in Chile, will feature a 39-meter mirror, the largest optical telescope ever built. Its tremendous light-gathering power and high resolution will enable detailed studies of distant galaxies and direct imaging of exoplanets around nearby stars. Radio astronomy employs massive arrays like the Very Large Array in New Mexico and the Atacama Large Millimeter Array in Chile. These facilities combine signals from multiple dishes to achieve angular resolution exceeding single telescopes. The Event Horizon Telescope, a global network of radio dishes, achieved sufficient resolution to image the event horizon region of M87's central black hole in 2019, producing the first direct image of a black hole's shadow. That image, showing a dark central region surrounded by a bright ring of emission from the accretion disk, confirmed decades of theoretical predictions. The shadow's size matched expectations for a black hole of M87's measured mass. The brightness asymmetry revealed the accretion disk's rotation direction and provided evidence for frame dragging effects near the event horizon. Gravitational wave astronomy, beginning with LIGO's first detection in 2015, opened an entirely new observational channel. Gravitational waves carry information inaccessible to electromagnetic observations, directly probing spacetime dynamics during extreme events. The detected merger waveforms test general relativity in previously unreachable regimes, so far confirming its predictions with remarkable precision. Future detectors will expand gravitational wave astronomy's reach. LIGO and Virgo are undergoing upgrades to increase sensitivity. Additional ground-based detectors like CAGRA in Japan and LIGO India will improve sky localization. The Einstein telescope, proposed for construction in Europe, will achieve 10 times better sensitivity than current detectors. LISA, the Laser Interferometer Space Antenna, will access lower frequency gravitational waves from supermassive black hole mergers. Its 3 spacecraft, positioned millions of kilometers apart in an Earth-trailing orbit, will detect gravitational waves in the millihertz frequency range. LISA will observe mergers involving black holes with masses from thousands to billions of solar masses, directly witnessing the types of events that might have contributed to TON 618's growth. These diverse observational approaches provide complementary information. Electromagnetic observations reveal matter's distribution and motion. Gravitational waves probe spacetime dynamics. Combining both enables more complete understanding than either alone provides. Multi-messenger astronomy, correlating signals across different channels, represents the frontier of observational capability. Theoretical work proceeds alongside observations. Advancing computer technology enables increasingly sophisticated simulations. Modern supercomputers can model galaxy formation including dark matter, gas dynamics, star formation, supernova feedback, and black hole growth in cosmological volumes containing millions of galaxies. These simulations reproduce many observed properties of real galaxies, suggesting we understand the basic physical processes involved. However, significant uncertainties remain. Small-scale physics like star formation and black hole accretion occurs at scales far below what simulations can resolve directly. These processes must be approximated through subgrid models parameterizing their effects on larger scales. Different parameterizations produce somewhat different results, indicating remaining theoretical freedom. Black hole growth in simulations depends sensitively on assumptions about how efficiently material reaches the black hole, and how effectively feedback regulates further accretion. Different models produce different black hole mass functions and different correlations between black holes and host galaxies. Matching observations requires carefully calibrated feedback prescriptions, but the underlying physical mechanisms remain partially uncertain. Understanding these processes requires studying them across multiple scales, from parsecs near black holes to megaparsecs for cosmic structure. No single simulation can resolve all relevant scales simultaneously. Instead, scientists employ zoom-in simulations focusing on individual galaxies with high resolution, cosmological simulations surveying large volumes at lower resolution, and analytic models bridging different scales. The interplay between observation, simulations, and theory drives progress. Observations reveal phenomena requiring explanation. Simulations test whether proposed mechanisms can reproduce observations. Theory provides physical insight guiding both observations and simulations. This triangulation gradually constrains uncertainties and deepens understanding. For TON 618 specifically, future observations might reveal additional details. Higher resolution spectroscopy could better measure the black hole's mass and spin. Imaging the host galaxy might reveal ongoing mergers or other unusual features. Detecting the galaxy at multiple wavelengths would constrain star formation and gas content. If TON 618's black hole actively accretes today, which seems unlikely but remains possible, multi-wavelength monitoring could reveal variability timescales and emission mechanisms. If dormant, detecting the host galaxy's stellar population would constrain formation history and evolutionary state. The black hole's spin, if measurable, would provide crucial constraints on growth mechanisms. Rapid spin suggests prolonged accretion from a stable disk, with material consistently adding angular momentum in one direction. Slow spin suggests growth dominated by chaotic accretion or mergers, where material arrives from random directions with cancelling angular momentum contributions. Current spin measurements for supermassive black holes rely primarily on analysing X-ray emission from inner accretion disk regions. Relativistic effects near the event horizon produce characteristic spectral features whose details depend on spin. However, these measurements require active accretion producing sufficient X-ray emission, limiting applicability to dormant black holes. Gravitational wave observations of supermassive black hole mergers will provide alternative spin measurements. The merger waveforms details encode information about both black hole spins and the final merged black hole spin. As LISA observes numerous mergers, statistical studies will reveal the typical spin distribution and how it evolves with redshift. These future observations will test formation scenarios. If ultramassive black holes formed primarily through mergers, their spins should reflect this stochastic growth with broader distribution. If growth occurred mainly through prolonged accretion, spins should cluster near the maximum value. The measured distribution will discriminate between scenarios. Beyond individual objects, statistical studies of large quasar samples reveal population properties. How does the quasar luminosity function evolve with redshift? What fraction of galaxies host active black holes at different epochs? How does the black hole mass function change over time? These questions require surveying thousands of quasars across cosmic history. Large surveys like the Sloan Digital Sky Survey have discovered hundreds of thousands of quasars, enabling robust statistical analysis. These surveys reveal that quasar activity peaked at redshift 2 to 3, then declined substantially. The brightest quasars, like TON 618, are extremely rare at all epochs but somewhat more common during the peak quasar era. The total mass density in black holes has been estimated by integrating over the quasar luminosity function and assuming reasonable accretion efficiencies. Results suggest roughly 10 Fersov to 10 Mabsnei solar masses per cubic megaparsec in black holes, matching estimates from direct black hole mass measurements in nearby galaxies. This consistency supports our understanding of quasar evolution and black hole growth. Climate models also constrain black hole growth indirectly. The accumulated radiation from all quasars throughout cosmic history contributes to the cosmic infrared background, diffuse radiation filling space at infrared wavelengths. Measurements of this background constrain the total energy released by quasars, limiting possible accretion histories. Similarly, high-energy photons from quasars interact with the cosmic microwave background through pair production, creating energetic electrons that inverse, Compton scatter additional CMB photons to higher energies. This process reprocesses some quasar emission into X-rays and gamma rays, contributing to the cosmic X-ray and gamma ray backgrounds. Observed background levels constrain quasar emission histories. These indirect constraints complement direct observations, providing consistency checks on our understanding. If models of quasar evolution produce predicted backgrounds inconsistent with observations, the models require revision. So far, reasonable models achieve acceptable agreement, suggesting we understand quasar demographics at least approximately. However, significant uncertainties remain, particularly regarding obscured quasars hidden behind dust. Optical surveys miss these objects, but infrared and X-ray observations can penetrate obscuration. The fraction of quasars that are heavily obscured remains uncertain, with estimates ranging from 20 to 80% depending on methods and selection criteria. Obscuration affects luminosity function measurements, because obscured quasars appear dimmer at optical wavelengths, causing them to be missed or placed in fainter luminosity bins. Correcting for obscuration requires understanding its prevalence and typical properties, introducing additional uncertainty into population studies. Future surveys at infrared and X-ray wavelengths will better constrain the obscured fraction. Wide-field infrared surveys like those planned for the Nancy Grace Roman Space Telescope will discover obscured quasars missed by optical surveys. X-ray surveys with missions like Athena will penetrate obscuration and identify hidden active galactic nuclei. These observations will refine our understanding of black hole growth and its relationship to galaxy evolution. The obscured phase might represent a crucial stage in black hole and galaxy co-evolution, occurring during major mergers when abundant dust temporarily hides the growing black hole. Understanding this phase is essential for complete growth models. The connection between black hole growth and star formation represents another active research area. Observations reveal correlations between black hole accretion rates and star formation rates in galaxies, suggesting linked triggering mechanisms. Major galaxy mergers can funnel gas toward galaxy centers, simultaneously fueling star formation and black hole growth. However, the relationship is complex and not purely correlational. Feedback from black hole accretion can suppress star formation by heating and expelling gas, creating anti-correlation on small scales or short time scales. Disentangling these effects requires carefully designed observations and sophisticated modelling. Simulation suggests the relationship varies with galaxy mass and cosmic epoch. In massive galaxies at high redshift, like TON 618's likely host, black hole growth and star formation might be more tightly coupled than in lower mass systems. The abundant gas available in the early universe could fuel both processes simultaneously. In the modern universe, conditions differ. Gas supplies are limited, mergers are rare, and most galaxies have transitioned to quiescent states. The tight coupling between star formation and black hole growth seen at high redshift has largely dissolved. Understanding this evolution requires tracing both processes across cosmic time. TON 618, observed during the era of peak quasar activity and vigorous star formation, provides a snapshot of conditions when coupling was strongest. Its host galaxy likely forms stars at prodigious rates, hundreds to thousands of solar masses per year, far exceeding the Milky Way's modest 1 to 2 solar masses per year. This intense star formation will not last indefinitely. As gas supplies diminish and feedback processes become more effective, star formation will decline. The galaxy will transition from a blue, star-forming system to a red, quiescent elliptical galaxy populated by aging stars. This transition, observed in galaxy populations across cosmic time, represents normal evolution for massive galaxies. The quasar will also fade as accretion diminishes. Feedback from the quasar itself contributes to shutting down further accretion by heating and expelling gas from the galaxy's central regions. This self-regulation prevents black holes from growing indefinitely and helps explain the observed correlations between black hole mass and galaxy properties. In its current state, billions of years after the epoch we observe, TON 618 likely sits dormant at the centre of a massive elliptical galaxy. The stars formed during its active phase have aged into red giants and white dwarfs. The black hole accretes only minimal amounts of material, producing negligible radiation compared to its quasar heyday. This fate awaits all quasars. The brilliant beacons illuminating the early universe eventually exhaust their fuel and fade into darkness. The black holes remain, silent monuments to past glory, waiting for occasional stellar encounters or minor mergers to briefly reignite activity. Yet even in quiescence, these black holes continue influencing their environments. Their gravitational fields govern stellar dynamics within the sphere of influence. Their masses contribute to the galaxy's total gravitational potential. Their presence affects the galaxy's response to interactions and mergers with neighbouring systems. And on timescales vastly exceeding the current age of the universe, these black holes will slowly evaporate through Hawking radiation, gradually returning their accumulated mass to the universe as thermal radiation. For TON 618, this process will require approximately 10-100 years, a duration so immense it defies comprehension. During this vast time span, the universe will transform beyond recognition. All stars will die, galaxies will disperse, even protons might decay. Black holes will be among the last structures remaining, slowly radiating away their mass into the void. The ultramassive black holes like TON 618 will be the very last to disappear. In those final moments, when the black hole has shrunk to perhaps stellar mass through billions of years of evaporation, Hawking radiation will intensify dramatically. The black hole will shine brilliantly in its death throes, converting its remaining mass to radiation over perhaps minutes or hours. Then it will vanish completely, leaving only dispersing radiation as evidence it ever existed. This represents the ultimate fate of everything that ever fell into the black hole. All the stars, gas clouds, planets, and perhaps even living beings that crossed the event horizon over billions of years will ultimately return to the universe as radiation, scrambled and thermalized beyond any hope of reconstruction. Information may be theoretically preserved in radiation correlations, but practically, the complexity and order that fell in emerges as simple thermal noise. This realization emphasizes both the impermanence and the incredible persistence of structures in the universe. Black holes, among the most durable objects imaginable, still ultimately succumb to quantum effects over sufficient time. Nothing lasts forever. Entropy always increases. The universe inexorably evolves toward maximum disorder. Yet the timescales involved are so vast that from any practical perspective, black holes are effectively eternal. The universe's current age is only 10 years. Even a stellar mass black hole lasts 10 years, exceeding the current age by a factor of 10^57. Supermassive black holes persist even longer, remaining long after every other structure has disappeared. For TON 618 specifically, its evaporation lies so far in the future that contemplating it seems almost meaningless. The universe will pass through countless eras, undergo transformations we cannot predict, potentially develop in ways we cannot imagine, all before this black hole's final evaporation. And yet, through physics and mathematics, we can predict with reasonable confidence what will happen. This represents a profound achievement, understanding processes occurring on timescales exceeding the current universe's age by factors of 10 to 90, predicting events that will unfold in a cosmos unimaginably different from today's. This predictive power demonstrates science's strength. By identifying fundamental principles and working out their implications through mathematics, we can extend understanding far beyond direct observation. We cannot witness black hole evaporation. We never will, yet we can calculate it, understand it, predict it with quantifiable confidence. This ability to transcend observational limits through theoretical reasoning represents humanity's unique capability. Other species observe their environments and respond to immediate stimuli. Humans alone construct abstract models of reality, derive predictions through logical reasoning, and test those predictions against observation. This process, iterated over generations, produces understanding extending far beyond any individual's experience. The story of TON 618 exemplifies this process. We observe photons that departed 10 billion years ago. We analyse their wavelengths, measure their energies, decode the information they carry about their source. Through spectroscopy, we determine the quasar's chemical composition, temperature, velocity and distance. Through theoretical modelling, we infer the central black hole's mass, the accretion disk's properties, the jet's power. None of this is directly visible. We never see the black hole itself, forever hidden behind its event horizon. We never observe the accretion disk's structure, too distant and compact for current instruments to resolve. Yet through indirect inference, combining observations with physical principles, we construct detailed understanding. This indirect approach characterizes much of modern science. We cannot see atoms, but we infer their existence and properties from countless experiments. We cannot observe the early universe directly, but we deduce its history from cosmic microwave background radiation and light element abundances. We cannot watch galaxies evolve over billions of years, but we reconstruct evolutionary sequences from observations of galaxies at different distances and epochs. Each inference involves assumptions and carries uncertainties. We assume physical laws operate uniformly across space and time. We assume our instruments measure what we think they measure. We assume our theoretical frameworks adequately describe reality. These assumptions, while well justified by accumulated evidence, remain assumptions nonetheless. Science progresses by testing these assumptions, seeking cases where they might fail, looking for anomalies requiring explanation. When observations contradict predictions, we refine theories, questioned assumptions, develop new frameworks. This self-correcting process gradually improves our understanding, asymptotically approaching truth without necessarily ever reaching absolute certainty. TON 618 initially challenged assumptions about black hole growth rates and formation mechanisms. Its tremendous mass at early cosmic epochs seemed difficult to reconcile with theoretical growth limits. This apparent contradiction spurred refinement of formation models, consideration of alternative growth mechanisms, and recognition that our understanding remained incomplete. Similar challenges arise throughout science. Observations frequently reveal phenomena not anticipated by existing theories, forcing revisions and extensions. Dark matter and dark energy, comprising 95% of the universe's content, were discovered through observations that couldn't be explained by known physics. Their nature remains mysterious, representing major gaps in current understanding. These gaps, rather than representing failures, indicate opportunities. They point toward frontiers where new discoveries await, where current theories break down and new physics likely operates. Scientists actively seek such anomalies, recognizing them as potential breakthroughs rather than mere puzzles. The information paradox surrounding black holes represents one such frontier. The contradiction between general relativity and quantum mechanics regarding information preservation has resisted resolution for decades despite intense effort. Its eventual resolution will likely require new physics, perhaps a complete theory of quantum gravity, fundamentally advancing our understanding. TON 618's singularity, like all black hole singularities, represents another frontier where known physics breaks down. General relativity predicts infinite curvature, but this prediction almost certainly indicates the theory's limits rather than physical reality. Quantum gravity effects likely become important before true infinities develop, but we lack the theory to describe what actually happens. These limitations humble us, reminding us that despite remarkable progress, our understanding remains incomplete. We've learned much, but mysteries persist. The universe continues surprising us, revealing new complexities as our observational capabilities improve and our theoretical sophistication advances. Yet this incomplete understanding shouldn't diminish appreciation for what we have achieved. From humble beginnings, limited to naked eye observations and mythological explanations, we've developed scientific frameworks capable of comprehending objects like TON 618. We've measured distances of billions of light years, calculated masses of billions of suns, predicted phenomena occurring on timescales of 100 years. This achievement results from cumulative effort across generations. Each scientist contributes pieces to an ever-growing mosaic of understanding. Individual contributions might seem modest, but collectively they produce the grand edifice of scientific knowledge we now possess. And the edifice continues growing. Current researchers add new pieces daily, telescopes gather more data, theorists develop new models, computers enable more sophisticated simulations. The frontier of knowledge expands continuously, revealing new territories to explore. For TON 618 specifically, future observations will undoubtedly reveal additional details. Better instruments will measure its properties more precisely. New telescopes might detect its host galaxy's current state, showing what the system looks like today rather than 10 billion years ago. Gravitational wave detections might reveal if similar black holes are emerging in the present universe. These future discoveries will refine our understanding, answering some questions while undoubtedly raising others. This pattern characterizes scientific progress. Solutions to existing mysteries reveal new mysteries requiring further investigation. The more we learn, the more we recognize how much remains unknown. This endless frontier ensures science will never complete its task. There will always be deeper questions to ask, additional phenomena to explore, further refinements to make. The quest for understanding represents an infinite journey, and perhaps that's appropriate. A finite universe fully understood might prove less inspiring than one containing inexhaustible mysteries. TON 618 stands as a testament to both our achievements and our limitations. We understand enough to recognize its extraordinary nature, to calculate its properties, to comprehend the physics governing its behavior. Yet it also reminds us of what we don't know, the questions we cannot yet answer, the frontiers still beckoning. This black hole, one of the most massive objects in the observable universe, exists both as physical reality and as symbol. Physical reality, 66 billion solar masses compressed within 1,300 astronomical units, blazing with 140 trillion suns' luminosity across cosmic distances. Symbol of the universe's capacity for extremes, of humanity's ability to comprehend despite limitations, of the eternal quest to understand our place in existence. We stand at a remarkable moment in history. For the first time, our species possesses the capability to observe the deep universe, to detect gravitational waves, to image black hole shadows, to trace cosmic history from the Big Bang to the present. Previous generations could only wonder about such things. Future generations might take this knowledge for granted. We occupy the transition, witnessing the revelations as they unfold. This privilege carries responsibility. We must preserve and extend this knowledge, ensuring future generations inherit not just our discoveries, but our methods and our spirit of inquiry. We must communicate what we've learned, making it accessible to those outside specialized fields. We must inspire the next generation of scientists who will push boundaries further, and we must maintain perspective, recognizing that scientific knowledge, while valuable, represents only one form of human understanding. Art, music, literature, philosophy, and countless other disciplines provide complementary insights into existence. A complete life requires integrating multiple perspectives, appreciating both what we can measure and what we can only feel. The universe revealed by science, containing objects like TON 618, proves far stranger and more magnificent than ancient mythologies imagined. Yet it remains fundamentally mysterious at its deepest levels, leaving room for wonder and awe. We understand much, but the ultimate questions: why does anything exist? Why these physical laws rather than others? What lies beyond the observable universe? Remain unanswered and perhaps unanswerable. Living with this uncertainty, acknowledging limits while pushing boundaries, appreciating knowledge while recognizing mystery, perhaps represents the appropriate stance. Not dogmatic certainty nor despairing ignorance, but humble confidence. Confident in what we've learned, humble about what remains unknown. TON 618 embodies this duality perfectly. We know it exists, we've measured its properties, we understand the physics governing its behavior. Yet its singularity hides mysteries. Its formation pushes theoretical limits, Its very existence challenges comfortable assumptions. It represents both triumph of understanding and invitation to further exploration. Our journey concludes here, having traversed 10 billion light-years to witness this cosmic monster. We've examined its accretion disk, approached its event horizon, contemplated its singularity. We've placed it in context, understanding its role in cosmic structure formation and galaxy evolution. We've considered its past, present, and unimaginable far future. The singularity remains forever beyond our reach, hidden behind the event horizon's impenetrable veil. We cannot observe it, cannot visit it, cannot know with certainty what lies within. Yet we've learned enough to recognize our ignorance, to identify where physics breaks down, to point toward future discoveries. This represents the scientific journey's essence, not arriving at final answers but continually pushing toward deeper understanding, recognizing each solution reveals new questions, accepting that the quest never truly ends. TON 618 marks one destination in this infinite journey, a milestone demonstrating how far we've come while revealing how much farther we might travel. The universe awaits continued exploration. Mysteries persist, frontiers beckon, and curious beings on a small world continue reaching outward, seeking to understand the cosmos that produced them, finding meaning in the quest itself. This is TON 618. This is what we know, what we've learned, what we understand about one of the most extreme objects in the observable universe. And this is merely one chapter in an endless story, the story of humanity's quest to comprehend existence. A quest that continues as long as curious minds persist in asking questions and seeking answers. The journey is complete, the story told, yet the universe holds countless more tales, countless more wonders awaiting discovery. TON 618 represents just one, extraordinary yet singular, in a cosmos filled with marvels beyond imagination. The quest to understand them all continues now and forever, driven by that most fundamental human quality, the need to know